Go ahead.
Yeah, so Panos Panayotaros is a full professor at IIMAS from the University Nacional, Autónoma de México, no? And he's going to give a talk, Law of Frequency Mode Interactions of Surface Gravity Waves in a Triangular Domain. Please go ahead, Panos.
Okay, thanks for the introduction. I will talk about work with Rosa Maria Vargas Magaña and also Morrison work with Edalí Guerra Velasco and Boris Persino Figueroa. And the general topic is surface gravity water waves in domains with inclined walls that we wanted to study, well, for a variety of reasons. One is coastal engineering, but also we can study some experimental situations, I mean, different scales. And we want to consider the model of free surface potential flow. Our modeling will be based on the assumptions of this, where you have a fluid that that's very simple in some sense, the simplest possible. It's incompressible, has no viscosity, and also there's no vorticity. So then you can assume that the Eulerian velocity is, that is the velocity at each point in the fluid is given by the gradient of some function that we call the hydrodynamic potential. And well, this is, you might think that this is very restrictive modeling, but it has been actually very successful, at least, well, over a lot of wide range of scales. It's not, it doesn't describe everything, but it offers an advantage that we basically can describe the fluid by the wave amplitude, so some function that describes where the surface is, and also this potential at the surface. And we can obtain some equations for these quantities from the hydrodynamic equations of motion. So the physics is in Euler equations, but it's a special case because it's no vorticity, and it's consistent with Euler equations. And once you put these assumptions, you eventually can obtain a partial differential equation for these two quantities. So the point is that we don't have to consider the velocity in the whole fluid domain. We only have to consider a potential on the surface. So basically we save one dimension, one spatial dimension. We can do that in 3 dimensions, but I'm going to consider only 2 dimensions today. So this is quite general. And so that has been tried perhaps 200 years ago by Poisson, and now there's a lot of literature. I mean, it has been one of the most successful models and gives rise to equations such as the Korteweg-Lebris, etc. So it's been widely studied, but not so much for problems with it's more difficult when you have a variable depth, because somehow, you have to solve Laplace's equation for any domain, and that is sort of can be done approximately, but there are some difficulties. But other than that, the other problem is that when you have this kind of geometry with where this is the flow here, and you have the fluid, and you have walls that are the walls have some inclination, then there have been some studies of the linearized problem, but not so much about the the nonlinear or weakly nonlinear waves. So this is what we wanted to examine, and also why. I mean, there's some difficulties that are kind of known, but anyway, and also in this problem, there's an extra motivation, because what we noticed with Rosa Maria when she was writing her thesis is that this study of normal modes is basically a linear problem. It's a linear problem where you consider the vertical derivative of this potential, or vertical velocity is proportional to this potential at the surface. That's a well-defined eigenfunction problem, an eigenvalue problem, but there is a bit of a problem of how to interpret the results you have, because the wave amplitude is obtained by this potential, and then but you realize that there is a bit of a problem of understanding where the free surface will intersect the wall. So if you want to study something like the beaches or something like that, where's the triple interface between the land, the water, and the air, then this result does not give you a clear interpretation. I mean, there are ways to get around this problem, but it's not very clear. And also, it's not very clear what equation was linearized in the classical studies, because the classical studies start from the 19th century. They do not say. But we use the fact that actually these classical theories provide a sort of scenario that is the following: that first of all, the fluid domain of the fluid at rest is some triangle, but somehow you include some larger domain, but that in this case is a quarter plane where the fluid can move, and also functions that are harmonic in this larger domain, and also that satisfy this Neumann boundary condition. This condition, that the potential has zero normal derivative at the walls of this larger domain, is actually physical. It means that the velocity here at the boundary can only be tangential. That is the physical assumption for inviscid fluids. So, and the non-trivial result of these linear theories is actually that these harmonic functions are eigenfunctions of that problem that I put here. So then we have so we want to follow this idea and try first to have derive a model for nonlinear waves, at least in this domain, the 45-degree domain, and then we can extend if possible, because it's not trivial even in this case. But the idea is actually that the modeling of the dynamical variables will be the hydrodynamic potential, and also the free surface, some function describing the free surface. But here we're introducing a new description which uses an auxiliary potential, and we integrate this potential over some epsilon. I mean, this is a second, not the physical time. It's and this potential, we integrate the gradient of this potential, and from this object we use the flow of this vector field to map this the free surface to some other curve, and this curve represents the free surface. So basically, we have to study the evolution of this vector field, whose time epsilon map gives me the free surface. Now, this description is complicated. It makes sense mathematically. It's not explicit, but it has some. It's not the only way to describe the free surface, but it has some advantages, that it preserves the volume, and also the endpoints of the interface will remain at the interface for all times, and so it has some kinematic properties that are useful, and they're encoded for any dynamics. And then we have, so essentially the idea is to expand the equations of motion that come from Euler equations for coefficients of these harmonic functions, one for the velocity essentially, and the other for the position of the interface. And then start some complicated procedure, because we have to also approximate. The problem is that here, when I tell you that you have to integrate a vector field at its time, well, we don't have an explicit expression, but at least we have some expressions that are approximate. For example, using Euler's an Euler method to integrate a vector field or something else. And also there is a small parameter, which is like the amplitude. And so we have an explicit expression for approximate expression for this, basically for this interface where this curve is. And we can then insert this approximation together with everything else to the full equations of motion that in the case of potential flow are Bernoulli's equation, and then start to approximate and then start to write an equation in powers of this small parameter epsilon, which is analogous to the wave amplitude small parameter. So there we can re-derive the linear theory only now at zero order in this parameter epsilon. Only now we have an interpretation that tells us where the free surface intersects the rigid wall, which is one of the original questions. And we see here we have actually, we can use, the problem is not trivial, the linear problem is not trivial, but at least it's known for this particular domain, the 45-degree domain. So this is work of Kirchhoff. And actually, I'm just mentioning that these normal modes have a sinusoidal part which dominates in the interior away from the boundary, but it also has some kind of exponential term near the edges of this domain, near the edges. And we have a dispersion relation, etc. Actually, the first mode is very simple. It's just the surface moving like that, up and down. And the higher order, the higher modes have this sinusoidal and exponential parts. So, and then we can do more computations to derive a nonlinear model which has the interaction of the modes, but you only go up to the quadratic interaction because we have to compute also some mode interaction coefficients. This is quite a lot of work. We have done it, but it is, and we have published these results, but it's still complicated. And also we have another, a sort of a PDE of which is equivalent to this model, which may also be useful for numerical studies. So the formulation appears seems possible for any domain, but the computations, for example, the frequencies and these mode interactions are only obtained for the 45 domain. They can be obtained for some other domains, but so of course there's a question of how to generalize. Now we see some nonlinear effects. We are a bit skeptical of our model because I mean there are a lot of models like that in not for this problem, but in general for water waves, for so-called Boussinesq or Witham-Boussinesq are similar because they have the exact linear part, and then they have some kind of quadratic interactions, but it's not immediate that this would describe the problem. But it's a first attempt, and we wanted to see some dynamics, for example, mode interactions, truncating to only two modes, actually truncating to the even modes that are in invariant subspace. And also we see some nonlinear effects, but the amplitude is very small because there is the possibility of blow up in finite time. So, and here is actually the free surface moving. Here is the triple interface moving up and down. But you see from the scale, this is supposed to be 45 degrees, but somehow the vertical scale is very small. Otherwise, these motions, we may have some blow up. It's reasonable we use some numbers. It's reasonable, but still not very satisfactory. Also, an interesting object, an interesting quantity to compute that we can compute is the height of this point of the interface. And we see how this height, this is for two modes, but as we include the amplitude, there starts to be some nonlinear effect of an asymmetry of the higher, the maxima and the minima. So, and this is some kind of effect that we obtain, but again, it's subject to further study. We can couple all this with a Hamiltonian formulation. I cannot go into that. We have a Hamiltonian model. This is, another paper, and we have some interesting things there. And also computation of nonlinear normal modes by using normal form and using now the non-Hamiltonian model, because actually we have a Hamiltonian model, but the first model doesn't seem to be Hamiltonian. There is a problem with these approximations when we use a lot of approximation to get to these models, and then that may destroy the variational structure. But now we can compute, however, some quantities such as the, for example, in this motion, which is this sloshing mode, we can compute nonlinear effects and how the frequency may be corrected, an amplitude-dependent frequency correction. That can be also be computed with these models. But the result is actually a very small correction, at least for this lowest mode. There can be other effects, but there can be, we need to add perhaps a cubic interactions. I think this needs to be done, but it's very, it looks difficult. I mean, it looks like a lot of work. Now, in a more recent work, which actually involved Dali and Boris, we return to the question of how to compute the eigenvalues and eigenvectors, that is the linear modes, for more general triangles, which again, as I said in the literature, there are examples for only a few angles, for only a few slopes, basically. 45, 30, the even modes are known, and some semicircular domains, very little. So we have a rather general method, but we consider for the time being only isosceles triangles. And here is, for example, we fix a horizontal scale for the free surface and vary this angle. And we use a conformal mapping, and so that the problem is written, basically the free surface becomes an interval on the half plane, and there we can write the eigenvalue problem after some manipulation as some eigenvalue problem for functions on an interval. And it involves a Hilbert transform plus some function that takes into account the triangle, that is a conformal factor that takes into account the shape of the of this domain. And then we can we see we have certain problems because this is the sort of the technical difficulty that the conformal map is not, well, it's not conformal over here at the corner, because everything is mapped conformally except well, the infinity and precisely the triple interface. So here we have some singularity in the derivative of this map, and so that seems to be the problem of this. But at any rate, we do get some results. We vary the angles from p/2 to 45. So we go from vertical walls, it's a semi-infinite domain, we close them, and then we get only to 45 degrees, and we study things in this range. And also we use the fact that we have exact results for this vertical walls and the 45-degree angle, which is also the 45-degree slope. And we see one effect is that there is an asymptotic slope of the eigenfunction eigenvalue times the index. By the way, this eigenvalue is the square of the frequency. And so the difference between consecutive values seems to be independent of the angle. This is our conjecture based on the numerical results. This is given for an intermediate value of phi between pi over 2 and pi over 4. And the other property is that there is an asymptotic shift of these eigenvalues of the square frequencies that does depend on the angle. And so, in fact, all the frequencies become smaller as we close the triangle in a monotonic way, and that depends also on the slope of the triangle. And we also have results on the normal modes. They're basically they're not as precise, but we see some effects, for example, on the slope near at the triple interface, etc. These are more quantitative. At any rate, we seem to be able to use. I'm ending now. Move beyond this triangle of 45 degrees. The formulation can be extended, but there's still a lot of problems. I don't have much time for all the details, but at least we can move ahead and at least in that direction. And also the conformal mapping allows us to study more general domains with sloping walls. So to summarize, I have given you this model. I at least mentioned basic ideas. There is also a variational formulation if one wants to use Hamiltonian methods. It's a well-known fact about the free surface potential flow that is a Hamiltonian system. But again, here, this formulation has a lot of difficulty. And also have started to use conformal mapping techniques for some of these problems, although they have their difficulties. For example, the accuracy is lost as the slope becomes smaller. So in fact, even before 45 degrees, we have limited accuracy, but at 45 degrees, we have this exact result. So I think that's it.
Okay, so these are your conclusions, Panos, no?
Yeah,
okay.
These are my conclusions. Yeah.
Okay, thank you very much, Panos. So are there any questions? Any question from the public? Okay, Panos, so what do you mean whenever you say weakly nonlinear model? So when your model will eventually become a strongly nonlinear?
Yeah, the weakly nonlinear is
physically.
This is the assumption that usually when you do this kind of modeling, you assume that the wave amplitude has some small parameter, for example, this eta. So this is the weak nonlinearity. And in the present model, the weak nonlinearity assumption is again that the amplitude is small, and that comes out of in a sort of not so immediate way when I have this vector field that is whose time epsilon map describes the location of the free surface, and I make this epsilon small. So then when I use this in the equations, I expand in powers of epsilon. So the linear theory is power 0, and the first order model is of order epsilon. So in that sense, the model is weakly nonlinear. It's something that has to do with this expansion that is used. Now, whether physically this is, usually nonlinearity means that weak nonlinearity means that, for example, the sinusoidal waves are slightly deformed when you don't start to see peaks when you have a traveling wave of sufficient amplitude. As the amplitude increases, I mean, you have some continuation problem there, but the surface starts to develop some kind of peak. That would be a a regime that of stronger nonlinearity, and then overturning effects like that. Here, these things are not. I mean, I don't think that this can be described accurately with this quadratic, at least, model. So in that sense, it's weakly nonlinear.
Okay. So the quadratic model is connected with the weak nonlinearity, right?
But there's a lot of experience because even weakly nonlinear effects have been studied and are known to lead to successful models. For example, the Korteweg-de Vries equation is actually a weakly nonlinear model, or certain Boussinesq or nonlinear Schrödinger models. They are all derived for small amplitude, and they're quite successful for predicting some things. They cannot predict overturning or I mean, what you see, the breaking of waves, but they describe other things like mode interactions, etc., modulation. So that's what we are hoping to get here, but so.
Okay, Hilda, please.
Hilda. Yes, Harold, thank you very much for this talk. I don't know, probably what you just said now after answering to Carlos had clarified a little bit, but will your model be able to find solutions like rogue waves?
It could find rogue waves, but I will tell you something about, for example, the nonlinear Schrödinger equation. It has rogue wave solutions.
Yeah.
But the assumptions of the derivation of the nonlinear Schrödinger equations in water waves are very small slope. So it has been useful, but people are stretching it. And that has happened with a lot of these models. Because that is, this is where it becomes a bit of an art. Mathematics cannot justify it. So here maybe there are rogue waves, but I can produce rogue wave-like phenomena with a linear problem if I just set my initial conditions. And then in a weakly nonlinear regime, there could be rogue waves. But we are stretching the model and we get something useful. I haven't done this rogue wave phenomena, but it could be examined. And another comment is that this is also from experience that you may need the cubic nonlinearity. I have only the quadratic. So because the quadratic nonlinearities, if you think of the Hamiltonian, the quadratic, the cubic Hamiltonian may not be, the energy may not be bounded, where in the quartic it may be bound. I mean, things like that. There are some mathematical properties that may make things better when you have. That's my experience in this regime in this scale. So you may need, we may need to do a little bit more. I mean, more work to add these cubic terms. It is a lot of work.
Yeah, I can imagine. But sorry to take so much time, but I want to ask you, I mean, I'm not in this field at all. I just remember when I was a student and I was studying fluid mechanics from the Landau books in those days. Yes. So, and we are talking about 60 years ago. So that's what I can remember. But what I remember from the book of Landau was that even, with the method that they had in those days, they were finding something that could look like a rogue wave. It was just by considering the bottom of the water, let's say, just going up, and not very much. And he was seeing that there were singularities. He couldn't solve in those days all the singularities, but he could already. We are talking about. Landau died in 1962, no? So in already in those days he was able to solve these singularities.
Well, there are different singularities. Breaking is different from a rogue wave. Breaking is basically when you have a very big slope. The slope becomes big. The amplitude is not big.
Yeah, it's a slope.
I'm not sure that this can be. What is very different here is that the tendency of waves to break is seen at the slope. It's seen at the beats, where the depth. So this is one of the difficulties of this problem, of modeling this problem, because, and I'm not sure we can model. My hope is somewhat different, that somehow these effects will be captured by some kind of dissipative mechanism that is only functioning near the beats, because there is breaking, but away from the beats. And this is the thing, that away from the beats, the problem is almost linear. But when the depth decreases, then the nonlinearity becomes much stronger. So, and this is actually a criticism of the small amplitude assumption. But, as a physicist, you might think most of the mass is in the ocean, is not on the beach. Although, so I mean, there's a lot of physical thinking behind all this mathematics, and that, because we want, for example, to study where is the interface in a big over scales. Where is what is the maximum height of the waves on the beach? But that depends on the whole ocean. So it is a bit of a challenging problem, I have to say. And this, the methods have advanced a lot. And actually, the thing is with Landau is that there is this separate line of work that starts. It's sort of a different school of thought on water waves with Stokes. It's Landau doesn't have much of that, but still that problem is not. Of course, engineers might tell you different things because they have pictures and Anyway.
Okay, thank you, Mayor. Thank you very much, Panos, for the talk. Okay, so if there is no more questions, we go to the next speaker, and the next speaker is Dr. Rosa Maria Vargas Magaña, who is a postdoc at the Department of Mathematics in the University of Bergen in Norway. And the title of her talk is Inertial Particle Transport Induced by Nonlinear Waves over a Gently Sloping Beach.
Yes, but thank you so much. But before I should share my screen,
Yes.
And I think I am presenting, so compartir esta ventana. Okay. Can you see my presentation or not? Not. Oof.
Not yet. We can listen you normally.
But my presentation is not on the screen.
No, it's not on the screen, right?
But now, can you see my? No, nothing.
Not yet.
No. Okay. Okay. Minimizar la presentación. I am pushing this button, the mute. Okay, compartir esta ventana. Now, agora você está compartilhando.
Not yet.
Not yet, but it's telling me that I am sharing right now.
We see your whole screen.
My whole
not
screen?
The presentation, yep.
But you see now, let's see. Now you can see my presentation because it's in my whole screen? No.
No.
Because you are sharing your entire screen. It's written here. So I stop sharing. What the God. Hello. Now?
Yes. Now
it's working?
Yes.
Oh, great.
That's okay now. Okay, please.
Okay.
Go ahead, Rosa Maria.
Okay. Okay. Thank you very much. And I hope after you follow this presentation, you can clear some of the ideas that arise during the questions that you did to Pano. And well, this is a work that originally began in collaboration with Henrik Kalisch here at the University of Bergen, and Fanet de Kin that did an internship with us. So our main goal today is to connect, well, the plan that we have with Panos is to connect the study of surface water waves on inclined walls with ongoing research on coastal waves on gentle sloping beaches and inertial particle transport. So the central goal, I will present a kinematic and dynamical model that reveals how surface waves influence the motion of inertial particles. And well, the big surprise at the end of this presentation is that theoretical prediction match very good with the field data that we collected during our recent field campaign. So before we keep going, I want to mention that I belong to the CIS program. This is a very ambitious postdoctoral program that attracted 37 researchers from around the world to come to the University of Bergen to develop knowledge around marine sustainability. And well, this is within this framework that I shift or expand my scope of research from the study of the propagation of waves in very controlled environments and studying isolate phenomena to the nearshore region in which there are many processes happening at the same time at different scales, at different spatial and temporal scales. So it's a more complex dynamical system, as you can see here. And well, in this work, I will focus in the nearshore region. And well, this is a highly dynamic region, and we can determine this region as when the waves start to break to the highest point the water reaches on the beach before it runs back. So Panos also mentioned this in his talk. So I also, in this atlas, you can see in this work, I will focus not just in coastal region, but in coastal regions with gentle sloping beaches. Now, in this atlas, we can see different nearshore slopes around the world, and in red colors indicate steeper slopes, while blue colors indicate milder slopes. So in my work, I am focused in this in this range of slopes, so not too steep, but not flat slopes. So, for instance, in Mexico, there are a lot of locations in which you can find the gentle sloping beaches, as you can appreciate in this close-up of the atlas. But in contrary, in Norway, the fjords are super steep. No? So this is an example of a gentle sloping beach. It's in the island of Sylt in the north of Germany. And I analyzed some data that from a field campaign that has been conducted in this place. So I will talk about this later. So I forgot to. Well, in this beach on the island of Sylt, you see these slopes. So within a distance of 100 meters, the depth goes from 0 to 3 meters. So also I am interested in waves that has a duration of frequency of seconds up to minutes. So, and as you can see in this chart, these waves are the ones that concentrate the largest amount of energy and are causing major impact in the coastal regions. So when waves travel from the deep ocean to the shore, they start feeling the topography. Can you hear me? Yeah. Well?
Yeah, we can hear you.
Yes,
oh, yeah.
yes.
And
yes.
you, I lost it? Okay. It's very weird to not see anyone. So, okay. Okay, they start filling the topography, and the waves become more phase coherent and quasi-two-dimensional. No, the waves they slow down and they get taller crest. This process is known as shoaling, and also the waves are aligned to the coastal line. So this reduces the lateral spreading of the waves and increases the fast coherence and producing wavefronts that align more with the shore. So all this together led us to the formation of these wonderful patterns that you can appreciate on the beaches, with well-organized wave trains and well-defined crest. The aims of this study is to gain insights into mass transport in coastal zones, extend the current set of equations that describe the transport of inertial particles within the linear regime, so for deep water. So the contribution will be to extend this system of equations to the shallow water regime in which all the nonlinear waves are happening. And also to introduce, to extend it to oceanic conditions, like infragravity waves that are long waves that are traveling locked in the wave groups of waves that are formed in a storm in the sea offshore. So, well, we will explore the dynamics of these particles when varying densities and sizes. So this is the outline of the presentation. I think I will skip it, otherwise I will not finish. So, but by the end of the presentation, the idea is that you will see how the signature of surface wave can be traced directly from the particles path. So at this moment, these are just paths that doesn't have any meaning for you, but the idea is that you can understand what is the signature of the wave that is propagating at the top and causes these paths. So let's start by talking about the field campaign. As I told you, this was conducted in this island in 2019. Buckley and Horchman and Stresser were the designers of this campaign, and Maria and Henrik, they introduced their input in waves. So this is a picture taken during that field campaign with a drone, and you see the incoming waves. Here is with the dash line. Well, this is the experimental setup. 2 cameras were mounted atop dunes overlooking the beach. So the field of view of the 2 cameras was the intersection of the overlapping intersection of this pink and purple region. And well, display or 6 poles were located in a vertical array, orthogonal to the incoming waves. And well, there were other gadgets installed for this field campaign because there were many goals for research. So, but in my case, my only raw data that I analyzed, I curated, and I am still working with, it comes from raw data, raw images coming from the stereo system of the 2 cameras mounted in the island. And with this is a small clip, but after performing a very time-consuming analysis and curation of the data set, we were able to extract 51 paths from the tracers deployed during that day. And with that, we were able to get paths that last from 2.3 seconds up to 3 minutes. So this is a unique data set that is very special, in which we can actually study fast oscillation, small groups, small frequency waves, but also the long frequency waves. And with this, we will be able to study the infragravity waves that I'm very interested to describe at the end of this talk. So For those that are not familiar with linear and nonlinear waves, well, this is the first image when we talk about linear waves. The first image that comes into our minds is like the sinusoidal waves, sinus and cosine functions that describe waves for small amplitude. But in reality, these kind of waves can just describe the waves that are very small amplitude in the ocean, when it's very calm. But in fact, the reality is that the waves looks a bit different. They have sharper crests and broad troughs, and in fact, these characteristics are more higher in the near shore. So the main difference is in the following the linear theory, we can describe the path of the particles induced by the movement of a linear wave, and we all have here that those corresponds to circular closed path. In the case of deep water, are circles, and when the particle fills the topography, looks like elliptic curves. But this is not true beyond the linear regime. When you get into the nonlinear regime, this means higher waves or nonlinear waves. Then the paths are not anymore closed paths. The particle experience a horizontal drift, and this drift can be done in the forward or backward direction of the propagation of the wave, depending on the mean surface water level of the wave. So the aim of this study is to extend our understanding of the trajectories of paths for inertial particles in the nonlinear regime. No? So in order to study this, we need to introduce the two non-dimensional numbers that will allow us to recognize in which regime we are living. So when you are a fluid particle and you are not, you basically follow the motion of the fluids that is happening. But when you have a finite size and density and shape, then there are other forces that plays a role here. One is gravity wave, the force of gravity, but the other force that appears is the buoyancy force that is opposite to the gravity, and also the drag force that is opposite to the movement of the particle. So Reynolds number tells you if the Reynolds number is low, this means that the particle velocity doesn't deviate a lot from the fluid velocity. And in order to know in which Reynolds number you are, you need to know the viscosity of the fluid in which the particle is lying, the size of the particle, and the particle and fluid velocity. Another non-dimensional number is the Stokes number. This basically tells you how particles, inertial particles, adapt to the typical movement or flow of the fluid. So if you have a low Stokes number, this means that the particle is strongly coupled with the fluid. So in order to determine which Stokes number, in which regime of a Stokes number you are, you need to know the typical particle response time, the fluid time scale, and the size of the particle and density of the particle. So to fix ideas, let's think about oranges. In fact, these were our surface tracers deployed at the island of Sylt, and we know everything about oranges, the density in particular, the mean size, etc. Also, we are describing water in the ocean, so we know the viscosity of the water and the density of water. So knowing these physical quantities of the particles and fluid that we are working with, in this recent work of Michel Di Benedetto and Nimish Puhara, they managed to distinguish that the Reynolds numbers in which some equation should the range of number in which the microplastics or tiny, microplastics can be described is within this range of Reynolds number from 10 to 100. So are not a small Reynolds number. So you really need to take this in consideration when you develop your governing equations. So these are microplastics. So the parting point of the setting of equation that we will use in our research comes from this paper, and in which they study, well, like we said, all the forces that play a role when you work with inertial particles. And in order to describe the acceleration of the particles at each time, in order to describe the paths, so you need to know the slip velocity. This is the difference between the particle and the fluid velocity at each time, and also you need to know the acceleration of the fluid. This is different from the acceleration of the particle. So all these forces are balanced, and velocities play a role in the movement of a particle, and they derive this very elegant and compact system of equation that captures buoyancy, drag, and settling effects. So this was our point of depart, and we look at this quantity that is in the equation, in the difference in the slip velocity, and this quantity takes in consideration the angular velocity of the wave that is propagating at top. So knowing this, it was our door to extend this setting of equations to the nonlinear regime. That we have developed a lot of work. The literature is very huge on this on this kind of waves, on solitary waves, conodal waves, and linear waves in the shallow water regime. And, well, we know the angular velocity for each case, and also solving the free surface potential flow evolution equation, or the water wave problem that Panos presented, you can get the horizontal and vertical velocities of the fluid at each time and each location. So with this explicit expression of the horizontal velocities of the fluid at each time, you are able to plug all this information into the governing equation for the shallow water regime in this extended framework, and you produce a very stable, efficient, and rich laboratory in which you can start studying the dynamics of particles at different sizes and different densities. The shape is, we are still just considering spheres. So we did many sanity checks, and we consider neutrally buoyant, negatively buoyant, positively buoyant, etc. And we saw for the simplified version of the model, in which we constrain the particle to lines in the surface, we consider very neutral, positive buoyancy, or buoyant particles. And then you see that at the beginning, when the particle is very small, behaves like a fluid particle. But when you start increasing the size of the particle, this affects, let's say, dramatically the path. Also, if you consider the full model, you don't constrain anymore the particle to lines in the surface, and you let the particle sink, then you see, again, this behavior when you start increasing the size of the particle. These Hertz paths are characteristic shapes of conoidal waves, and this, in this slide, I just wanted to present, well, the behavior of conoidal, when a conoidal wave is traveling in the wave. What?
You have 5 minutes, Rosa Maria.
Oh, okay. Then you see that here we are considering a set down. This means that the mean surface, mean water level is below, and you see that the particle is moving forward. It's not moving It's moving backward. Well, you can do all this analysis, very detailed analysis, but the most important thing that I wanted to present is the infragravity waves. So the main factory of wave generation of waves in the ocean, in deep water, are the storms. So how the storms create a very nice wave package of waves that travels and reach the coast. This is the next. When the storm starts, it's a very energetic event that produces a lot of different waves that have different frequencies and travel in different directions. But there is this wave-to-wave interaction that if you find waves, here, and they start like moving away from the storm. They are moving away because in deep water, waves are dispersive. So waves of different frequencies travel at different speeds. So longest waves travel faster than shorter frequencies wave. So there is this wave-to-wave interaction that produces higher amplitude waves. And if you leave the days, you look at the ocean after a few days, you start looking very well organized wave groups of waves that are traveling at almost the same speed like this. And this eventually reach the coast. And then the idea is that we model this superposition, these wave groups, and we obtain like the trajectories that they are creating on the particles. And the thing is like we see the fast oscillation in each turn that the particle gives, but also we see the low frequency wave that tells you that the waves go in the forward or background direction and then start turning along his way. So like that. And well, the final, I don't know, I have a minute. Well, the idea was to match the theoretical findings with the data, field data collected from the island of Sylt. And the important thing was we match the trajectories. But this is the thing. We managed to analyze the time series of the surface elevation and detect the frequency of the fast waves that were happening at the island of Sylt on that day were 5.5 seconds, and the the lower frequency wave that appears and expresses like a variation of the mean in the mean water level, that this happens in a periodicity of 1.1 minute. And with this, we were able to model the trajectory and look at the path, and it matches qualitatively and quantitatively the data collected that day. So I think this is everything. Thank you.
Thank you very much, Rosa Maria. Thank you so much for your nice presentation.
It was a bit fast.
Yes. So,
But,
are there any questions? Okay, I would like just to ask, so seemingly there is a transition between conoidal waves and solitons, no?
yeah.
As you mentioned, no? So which model do you refer to in this context?
The KDB.
The cartographic phase.
Conoidal waves are the nonlinear periodic solution of the KDB equation, like the classical one.
I see.
And the solitary waves, these papers uses this KDB equation.
The KDB equation, okay. Thank you very much. Okay, I guess there is one question from Elbert. Please, Elbert, go ahead.
Very nice presentation. Very, very, very nice work.
Thank you.
Related to experimental observation, have you able to check this experimental observation with your results and how it works like that?
Regarding the experimental observation, what did you...
Yeah, about this phenomena that you describe in your equation, your model.
Yes, everything. Oh, in fact, I am learning in this process. I am learning from the data analysis. First, I extracted the Lagrangian paths from the tracers. And in fact, the goal was just to test a wave-breaking criterion. But then I realized these time series were like, if you apply some methodologies from financial settings or from machine learning, you can extract hidden information from the waves. And this is the thing that we are getting. After analyzing the surface data elevation time series, is that I realized that you were able to describe the infragravity waves, because so far the waves they use is like using the envelope or the Hilbert transform to find the envelope, but it's not the way. They never curated the data set as I did in order to really clear the noise from the time series, because it's very noisy and so you really need to clear the noise and do some work there.
Okay, thanks so much.
Okay, thank you so much,
Okay.
Rosa Maria, for your nice presentation. Okay,
Thank
so
you.
we are a little bit short of time, so
Yes, of
we
course.
go to the next speaker. Thank you so much. Next speaker, who is Kevin Peralta, who is just a recent graduate, a recent PhD graduate from the Instituto de Física of the Universidad Autónoma de Puebla, in Puebla. You see, and the title of his talk is Survival Probability in Random Network Models. Please, Kevin. So I guess we can see you, but we don't see your presentation. Okay, perfect. Okay, Kevin. So go ahead. Thank you so much. We cannot listen to you. I guess your microphone is off. No, we cannot listen to you. Or I cannot listen to you in any case.
Hi?
Yeah. Okay. Yes, okay.
Great. Well, thank you very much for the introduction. The last part of my doctoral thesis work was about network dynamics, in particular about the survival probability in random network models. This work has been done in collaboration with my thesis advisor, Jose Antonio Mendez Bermudez, who is also a professor at Instituto of Physics, IFUAP, in Puebla, Mexico. So the aim of this study is to have a framework for the study of network dynamics. The second aim of this study is to study the survival probability of an initial state of a quite known random network known as the Erdős-Rényi network model, being represented by the orthogonal random weighted adjacency matrix in the context of random matrix theory, in particular taking into account the Gaussian orthogonal ensemble. As part of this study, we want to characterize the behavior of the survival probability applied in this network model. So, as part of this talk, first I will talk about the adjacency matrix, which is the mathematical tool we take into account for the study of this model. I'll talk about the random matrix theory, in particular about the Gaussian orthogonal ensemble. Then I will talk about the survival probability and its stages and how it is applied then to the Erdős-Rényi network model, where we characterize the initial phase decay, a power law decay of the survival probability and its correlation hole. And finally, I will give some remarks on this work. So first, the adjacency matrix, as I said, is the mathematical tool to extract the skeleton of a graph or a network. So this matrix is a binary square matrix, which takes into account the adjacent connections between pairs of nodes. So here, for example, we have a small graph with nodes A, B, C, and D. And as we extract its adjacency matrix, we place numbers 1 every time there's a connection. So for example, node A is connected to node B and D. Therefore, entries AB become 1 and entries AD becomes 1. So notice that this matrix is symmetric, okay? Because entries BA become 1 and entries DA are also 1. So what we have here is a binary matrix which is symmetric. And one particular characteristic that we can extract from the adjacency matrix is the degree of a node. The degree of a node described by this equation is the number of edges or vertices that every node has. So in this particular case, the degree of the A node corresponds to 2 because it's connected to node B and D. The degree of node B is 3. The degree of node C is 1, and the degree of node D is 2. So I got to stress here that the degree is a quite important measure and quantity of a graph, as we'll see some slides ahead. So another way to represent a graph is through the weighted adjacency matrix, which is quite similar to the previous one, but now instead of having only ones in the matrix, we have weights, which can be quite relevant in the modeling of complex networks, since they can signify the tie strength, the intensity, or the capacities that there are between nodes and the interactions, okay? So in this case, we have a graph, okay? We have the weights, and instead of having ones, we have the weights in every entry, as we see in equation 1. So how can this be matched to random matrix theory? Okay, so in particular for this study, we take into account the Gaussian orthogonal ensemble. So what's the idea behind random matrix theory? Random matrix theory in physics comes from the idea that when we have a quite complex quantum system and we cannot extract fully Hamiltonian, we take into account symmetry properties that can be modeled by random matrix ensembles. Okay, so in this particular case, for our study, the core idea of using random matrix theory ensembles is to study the properties of random matrices whose entries are random variables, and that can take into account or take into account relevant properties, in this case of random networks. So the definition for this ensemble, the GOE, is an ensemble of n times n real symmetric matrices, which have independent entries taken from a Gaussian distribution, where the entries of the main diagonal are centered with mean 0 and variance the double of the off-diagonal elements of the matrix, as we see in these equations. So as an example, we have here a 3 times 3 GOE matrix. The main diagonal is filled with random numbers with variance the double of those of the off-diagonal. Okay, so what's the key feature of this ensemble? That this ensemble is invariant under orthogonal transformations. That's why it's named. But also in physics, the originality of this ensemble is that it can model time reversal symmetry systems. So up to this point, we know that we can have weighted adjacency matrix representations, and GOE preserves the symmetry and the orthogonality. So matching these two ideas, we can define a GOE-like adjacency matrix, which preserves the orthogonality of the GOE formulation. So in this case, instead of placing only ones or just weighted some weights, we take those weights in a similar way as the GOE does. So we take random numbers from a normal distribution every time there's a connection between nodes. And for the main diagonal, whether there's a connection or not, we place also random numbers, but with the double variance from the off-diagonal elements, and 0 when there's no connection at all. So here we have a random network. This is an Erdős-Rényi network with 50 vertices. And when the probability of connection P between nodes is 0, this representation has, by definition, the adjacency matrix filled with random numbers. This is the known matrix elements of the adjacency matrix. So as P increases, connections start to appear, and the adjacency matrix becomes filled with random numbers. Okay, so as we progress with this, we observe that when P becomes 1, the adjacency matrix is full. Okay, it's filled with random numbers. So under an ensemble study of networks characterized by a parameter P, we can have an ensemble of random matrices that resemble or have as limits random matrix theory ensembles. So when P equals 0, this adjacency matrix, this orthogonal adjacency matrix, takes the Poisson ensemble limit. That is, we have only a diagonal with random numbers. But when P equals 1, what we get is the GOE ensemble, because the matrix is full. Okay, it's random at all. But at intermediate stages, what we get is what we call a diluted version of the GOE. Okay, so what's happening with the survival probability? The survival probability is a measure that can or reveals how does the information propagates or survives from an initial state in a system. So recalling that now we have a weighted GOE-like adjacency matrix for any graph that we have in this type, we have the GOE limit. So the survival probability can also be analyzed from the GOE perspective. As I said, when the system is quite difficult to understand what's the shape, what's the form of the Hamiltonian, but we only know its symmetries, we take into account Hamiltonian that is described by a GOE matrix. Okay, so I got to say here that the survival probability measures the probability of an information packet that remains within in its initial state. So considering now that the system is quite difficult to analyze, we substitute it for a GOE matrix, and we consider the existence of a fictitious basis in which every GOE matrix is written. And we take into account an initial state that is characteristic of the localization study of the whole system. That is, we take into account an initial state at the center of the energy bulk of the, in this case, of the GOE matrix. Okay, so but we can rewrite this initial state as a projection of the eigenstates of the GOE or this Hamiltonian, this GOE Hamiltonian. Therefore, the survival probability can be written in this form, where, as we can see in this equation, these terms correspond to the projection of the initial state onto the eigenstates of the system. What we have here is that the survival probability is the Fourier transform of the local density of states described in this equation. As we said, we took into account an initial state at the center of the ball, which is characteristic of the localization of the system. In this case, and as the random matrix theory recipe, what we have for this initial state is that the local density of states have a semicircle form, which is called as the Wigner's semicircle law, described by this equation. Okay, where sigma ini is the energy distribution spread variance of that initial state. So what we expect to have in the behavior of the survival probability for the GOE case. Well, what we have is that first we observe an initial exponential decay due to short time dynamics. Then we have a damping slower decay described by this t to the minus 3 decay, which is damping. Then after the tallest time, which is the time where we observed the correlations in the system, we have another phase which is known as the correlation hole. And then as the time passes, we get to the long time saturation, which corresponds to the inverse participation ratio of the system. That is the number of states that create the state. Okay, so okay, now that was the framework of this study. Now, how can we apply this to the survival, to the study of random network models? First, the Erdős-Renyi network, which I showed you in the previous animation, is a graph characterized by two parameters. First, n, which is the number, also called size of the network. That's the number of nodes that the network has, and p, which is the probability of connection between pairs of vertices or nodes. This model has a well-defined, analytically defined average degree, which is n times p. And here, just to depict the idea of our study, we want to study the Erdős-Renyi from the isolated phase, which is when p equals 0, to the complete phase when p equals 1. So, as I mentioned before, the local density of states is the survival probability is a Fourier transform of the local density of states. So if we know the shape of the local density of states, we know the shape of the survival probability. In some previous studies on the local density of states of the Erdős-Renyi network, what has been found is that there's a critical value up to which the local density of state shape does not deviate from the semicircle law, the Wigner's semicircle law, which we have in this case. So we have three sizes of the network, of the Erdős-Renyi network, and we observe that when PC is when P is equal greater than PC, this critical value, the local density of states does not deviate from the semicircle. But when P is much smaller than this critical value, what we observe are some peaks that correspond to Gaussian distributions, quite normal when the system has to few components forming it, and some deviations from this semicircle law. So, since the local density of states has a similar form to the GOE case, we expect to have the shape of the survival probability being quite similar to that of the GOE ensemble when P is considerably large. So in this case, I'm showing you an analysis for an ensemble of 50,000 random networks, okay, for different values of P and a network size of 1,000. So, like as I said, for values larger than PC, this critical value 0.1, we observe in panels B and C, we have a similar form to the GOE case. But for when P is much smaller than that critical value, what we have is this particular power law decay, okay, before getting to the correlation hole, which is not expected from simply from the shape of the LLOs. It's important here to say and to stress that this time evolution is not dictated by Hamiltonian, but instead we dictate this time evolution by the adjacency matrix previously described. Okay, so in this study we perform a numerical diagonalization where we get the eigenvalues, the normalized eigenstates, and the projections of the initial state onto the eigenbasis of every adjacency matrix ensemble. So when we plot the survival probability for 4 different sizes, 250 to 2000, increasing from top to bottom, we observe that these curves fall one on top of the other before saturation values. That's why they deviate at larger times. And we analyze this particular case. So it's well known that the first approximation of the survival probability is given by equation 4, where sigma ini is that's the energy distribution, the variance of the energy distribution of the initial state. Okay, that's the variance of the initial distribution. So in our analysis, when we plot this standard deviation in terms of the probability of connection in this panel G, we find that there's a power law relation, which is described by equation 5. So for the Erdos-Renyi network model, the fast initial decay is characterized by the average degree. So what we observe in every panel is a green curve, which corresponds to equation 6, and for every and where the degree is taken for every case in this equation. So in many-body quantum localization, the analysis of this power law decay is quite relevant. And in this analysis, people has taken into account the correlation dimensions. First, they take into account the correlation dimension D2, which is the study, the size study of
You have 5 minutes,
thank you
Kevin.
Okay, so the study of the eigenstates in a window center at the half of the spectrum, which are described by equation 7, and also the correlation dimension of the initial state, which is given by the projections of the initial state onto the eigenbasis. So in the red dashed lines, what we observe here in every panel is the decay depicted by D2. In this case, T to the minus D2. And as we observe in panels B, C, and D, before saturation times, the red lines describe better the decay, the power law decay. On the other hand, the blue lines correspond to the decay given by D2 tilde. So as we observe in panels E and F, this is a better descriptor of the decay. So what we get here is that for longer times and greater values of the average degree, the correlation dimension of the initial state D2 tilde is a better descriptor. And for short times and small values of K, D2 without the tilde is a better descriptor of the power law decay. So also in many-body quantum localization, in order to have a broader analysis and a more general analysis of the survival probability, they investigate the time average survival probability described by this equation. So what we have here is that in the red lines, we depict the decay of t to the minus d2. And what we have is that d2 is the descriptor of the slow decay as we observe in every single panel. Okay. What we have is that d2 is the descriptor of the slow decay for this quantity. So in studies, in order to detect the integrability to chaos transition of disorder system, they use the correlation, people use the correlation, the relative depth of the correlation hole described by the equation 10. So in our analysis, what we have here is that we have the correlation, the relative depth of the correlation hole described for different sizes of the Erdős-Rényi network and different values of p. So we observe a transition, as expected, from localized systems to chaotic systems as they reach in the magenta line the GOE prediction. That is, as we recall, the when the ensemble is full of random numbers. Okay, so as we plot this in terms of the average degree, we have an universal curve since every size fall one on top of the other. So this permits us to propose an heuristic equation described by equation 11 in terms of the average degree. So notice here that we get universality since we have an equation that describes this behavior. So finally, some remarks. This work has to do with network dynamics, in particular the survival probability of Erdős-Rényi networks as a general framework to study complex and random network models. In this case, Erdős-Rényi networks exhibit an initial fast decay followed by a power law, and we were able to characterize the fast initial decay of the survival probability in terms of the average degree. We also characterize the power law decay by using the correlation dimensions d2 and d2 tilde, and we also got an universal curve of the relative depth in terms of the average degree. So, I guess that's it. Those are my final remarks. Thank you.
Okay. Thank you very much, Kevin, for your nice presentation. Okay, so we go to a question, please. Are there some questions? The panel.
I don't seem to be able to. Okay, here.
Yes.
Okay.
Please, Hilda, go ahead.
Yeah. Thank you very much. Very interesting talk. But I have some questions because I really don't understand very well what you are doing. Let's put it this way. While you refer to a GOE distribution, you are telling me that the distribution of the values of the matrix of this case you are calling the adjacency matrix, which, for instance, in the case of localization that you mentioned at the end, they were essentially they were essentially the values of the energy levels, let's say. They were energy distributions of the particles. Now, you are trying to use that as a random network. On the other hand, a random network, as those who do random networks classically usually talk about, is they refer to the topology of the system, or they may refer to the links. I don't know, maybe in your case the links, or maybe in your case it could also be a random distribution of the dynamics of the system. So the point is, my point is, as you have noticed, I have not understood much, is I want to what I want to know is what kind of a system are you describing by a random network, while what you have is a random distribution of eigenvalues? I mean, I don't know if I'm clear because I don't have it clear in my mind. Okay.
Okay. No, okay. It's okay. Yeah, I understand. Okay, the system I'm trying to describe is how does, let's put it this way, information of an initial state of a network, like a network like this one.
Excuse me, you mean that each node is represented by a quantum state? Is that what you're telling me? The state of each node is a quantum state?
Yeah, we can think it that way. Okay. Yeah, that will be the idea. But what we're analyzing here is first that this graph is not like a simple graph, because every interaction is assigned a random number. Okay, so we do this and we repeat this for a large amount of networks. So we have an ensemble, and we can then have a statistical average, okay, of the properties of the network. So by doing this, now we take into account an initial state. It can be of any node. Okay, it's not in a specific node. That's why it's general. And then we study what's the probability of that state to survive in time, like a quantum state.
Yeah.
Okay, that's the why we take weights and we do not take, like I showed previously, this binary matrix. Well, that's because this is a framework, okay, to study complex networks. Okay, in network science literature, there are many instances where the Erdős-Rényi is taking like a basis and a model to get some insights in real data systems. Okay, so here is a general approach, because we are not choosing only connections, but we are also adding weights to them. So that makes it general, because that way can represent many different things. I don't know if that answers your question.
Well, yeah, partly. Thank you. Welcome. Yeah.
Are there any more questions?
I'm sorry, I don't have my microphone. Okay, Albert. So I mentioned that thank you very much, Kevin. Thank you very much, everybody, for your nice presentation. Panos, Rosa Maria, and Kevin. Albert, so are you there?
Thank you.